So now that we are done with talking about different ways to synchronize multi-threaded and multi-objects applications. So let's look a bit about at deadlocks. You have studied a bit about deadlocks, but let's iterate a bit on what they are, because they are pretty nasty when it comes to the operating system. So it's basically if you have resources that are contended and there's just not enough of them. So any passive thing needed by a thread to do its job is the resource, of course. And a deadlock is basically occurs when you have circular waiting for the resources. So looking at, for example, this example, you have a thread A and thread B. Lock each thread tries to acquire two locks, and thread A acquires lock 1 first, and thread B acquires lock 2 first, and then they basically try to acquire the opposite locks after the first one. This is the pretty simple case, and then you end up in a circular deadlock. But you can have it in a system like this. If you have a bidirectional bounded buffer, for example, so you don't see any threading here, but you just see that buffer 1 tries to put data, thread A tries to put data in buffer 1 and retrieve data from buffer 2. But in the beginning, it tries to put two pieces of data in buffer 1. While thread B tries to do the opposite. It tries to put data in buffer 2 and basically get data from buffer 1. If both buffers are full, then basically when buffer 1 starts trying to putting in data when thread A tries to put data in buffer 1, then the thread is full, so it has to block until somebody empties the thread. But then since it's only thread B that can empty the block, and it is now basically also waiting for buffer 2 to empty a bit, then you get a deadlock, although you do not see even a single line that talks about locking over here, because each one of them will wait for the other to empty its bidirectional bounded buffer. It can happen with if you have two conditions and a condition, two locks and a condition variable. So this one acquires thread A tries to acquire lock 1, thread B tries to acquire lock 1, thread A wins. Thread A acquires lock 2, thread B is still locked, it cannot do anything, and basically thread A starts by checking on the condition variable, and it waits on lock 2. Okay, so it basically it has acquired them in the correct order. You have lock 1 dot acquire, lock 2 dot acquire, it already acquired them, but then it needs to wait on a condition variable. While thread B is the only thread that has a signal to break this waiting. Okay, so the condition that signal lock 2 occurs in thread B, but thread B is blocked since both locks are now acquired by thread A. It can happen if you go to India or to Egypt or to Kenya or one of the beautiful countries where people drive with very little laws. You end up in these deadlock situations everywhere, basically. I mean, it's quite common, and then it needs special skills to actually break these deadlocks. You typically have someone going down from the car, signaling to the cars to basically, okay, you stop, you go, and so on until the deadlock is broken. And sometimes people are just stubborn, and you end up in these situations for hours and hours. And I have happily lived in two of these countries that where you need this skill. There's the dining philosophers in the slides I put online. The author of the book called them the dining lawyers. This is the first time I actually use most of his slides because they were good for this section. But he calls them dining lawyers because the author of the book has a bachelor's in philosophy, and he thought that lawyers are just stupid. And well, I happily changed that back to dining philosophers. So you have philosophers sitting around the table trying to eat spaghetti or something, And well, they have chopsticks, and everyone, or a fork and knife, or two forks, or any two pieces of resources that are needed to eat. And if everybody starts by picking the one on his left hand side, then you end up in a situation, if you look at this figure, where there are absolutely no chopsticks empty and no one can eat, and all of them will starve and die. So this is basically a classical problem in computing science, and in having basically the dining philosophers problem. So the necessary conditions for having a deadlock is that you have limited access to resources. If you have infinite resources, then there is just no deadlock. If everybody can acquire the memory, or different memory, or operate in different memory, then there will be no deadlocks. There is no preemption. That is basically nobody breaks the deadlock by its own, because if you have, for example, you can build an algorithm where you basically say that, okay, if I wait on this thread for more than 5 seconds, I'm going to break, which is a valid way to basically break deadlock. And it's actually, I mean, if you look at computer networks, you have the Sysma CD protocol, which basically and Sysma CA protocols, which basically on the Ethernet. And the way, since you have a contended resource also there, you basically have the network line. You cannot really run a lot of packets on the same wire. Just, well, it's electricity, and what you're running is basically plus 5 volts and minus 5 volts, or plus 5 and 0, depends on the signaling, but that's another thing. So if you're sending packets, no one else can send packet on the same wire. And the way that they basically break the deadlock is that they have a collision avoidness algorithm, which basically probes the line, and if the line is contended, if someone is there, then it starts adding a variable random amount of time before it sends, so that since everybody trying to access the line adds a random variable, then you basically end up in a situation where everybody tries to run at a different point in time. Well, there are multiple independent requests that need to wait while holding, and there are circular chains of requests. And the dining philosophers meet the necessary conditions because you have a limited access to resources. You just have to the number of chopsticks is equal to the number of people on the table. There is no preemption. If you take a chopstick away from a lawyer, from a philosopher, then they are no longer in a deadlock. So if they can communicate, and one of them can hand the chopstick to the other, then you basically can break the deadlock. You wait, and they all wait until some resource is available. And you have a circular chain. One left hand, so everyone is waiting to the one on the right-handed, on his right hand to finish, while he's not going to finish. And there are multiple ways to break the deadlock. In this case, one of them would be to add an extra resource, so add just an extra chopstick in the middle of the table, and then only one of them will be able to grab it, right? You can even have the same number of chopsticks, but remove one from the circle and add it to the center of the table. And then, since the rule is that you cannot, you always acquire your left hand side chopstick first, and one of them will not have a chopstick on his left hand side, so he cannot do anything. And then basically the others one of them will acquire eventually two of them. So there are multiple ways to break these locks. I'm going to sneeze, so I am going to stop.